This video covers Faraday's law. Now, the magnetic flux is defined as the flow of the magnetic field through an area of space. Again, flux is going to be represented by a sigma, which is this letter here. Again, this is flow, or magnetic flux. It's going to have units of Tesla meters squared. That means the equation must include Teslas, which are magnetic fields, and area, which is meters squared. Again, this cosine tells us that the angle between the magnetic field and area has to be parallel. Now, area is not a vector, but the normal vector, which is perpendicular to the surface, is a vector. So we're going to be using that as our area vector. The most important part here is that if a surface is involved, angles are measured with respect to the normal. We'll see an example of that next. In this case, my magnetic field and my normal vector are not parallel to each other. So we want to get them parallel. Here you have your normal vector that's going off to the right. And my magnetic field goes off in this direction. So if we wanted to find the parallel component, we'd have to find the x component of our magnetic field, which in this case happens to be b cosine theta. But you need to be careful because that's not always true. Now we're going to use this flux to calculate our electromagnetic induction. Electromagnetic induction is the process of creating or inducing a potential or EMF which provides the necessary electrical pressure potential to induce a current in a closed loop of conducting material. Again, we saw in our last video that a loop moving in a magnetic field causes current. Well, we're going to see how changing flux also does that. So again, we have to have a changing flux. This is the most important part, changing being the operative word. Now, let's look at changing flux. Again, flux has to do with the magnetic field and the area. So there's different ways to change the flux. One way would be to change the strength of the magnetism by moving the magnet toward or away from the wire. Again, that changes B. Or you can leave the magnet stationary and move the loop away and from it, again, still changing the strength of the magnetic field at a certain point. If the magnet is a current-carrying wire, changing the amount of current will change the strength of the magnetic field. Again, still changing B. But you can also change the area. And by that, you're going to see if you turn a wire loop so that less magnetic fields are able to pass through it, then you're changing the area, therefore changing the flux. Now here is Faraday's law. This calculates the EMF, or the potential, that is induced by a changing flux in a loop of conducting material. Again, here you have your flux variable. Our sigma means EMF. And this law is written for a single loop of wire. So if you have multiple loops, you need to multiply this by the number of loops involved. Here we're asked to determine the flux. Again, it's telling us that the rectangular loop is perpendicular to the magnetic field. But that just means that my normal vector is already in the same direction as my magnetic field. So the angle between the normal and the magnetic field is 0. So we don't even have to worry about the cosine here. So plugging in all my numbers, I get 0.0672 Tesla meter squared. Here's the continuation of the problem. Here, the magnetic field is being moved to a very far distant away, a very distant point. That means that my magnetic field is essentially 0. So if I want to solve for my induced EMF, my flux when my magnetic field is equal to 0 would be 0. My magnetic flux at the beginning was 0.067. And the time it takes for this to happen is 5 seconds. So I get 0.0134 as my potential, or induced EMF. In our previous videos, we only said that we were moving a rod into the field. Now we're going to move an entire loop of conducting material in and out of the field. Now I want you to think of the loop as full of positive charges. So if the loop moves to the right, then so do the charges. Right now the loop is not in the field, so nothing's happening. Using your right-hand rule, when the loop enters the field, now we have a force upwards that causes a current to flow in the direction of these blue arrows. So right now, our charges are flowing in the counterclockwise direction. The interesting thing is that when this loop is entirely in the magnetic field, that force, that upward force, is acting on all of the positive charges. So there's actually no current flowing at all. But when our loop of wire moves out of the magnetic field, then you have, again, using your right hand rule, see that the charges start to move again. And we now have a current, but now it's in the clockwise direction. Again, make sure that you practice the right hand rule in these examples. So here's a summary of what's happening. Now, again, this is situational. It does depend on the direction of the magnetic field. If the magnetic field were flipped, everything would be in the opposite direction. Now, we've seen the first equation before, this one. But now we introduced this one. Again, the left one is definitely easier, and it helps if you understand where it comes from. So let's say that our area is increasing. That means we're moving it into the wire. As area increases, again, you're going to see an increase in potential. Here, if my width increases, that's still an increase in potential. But now we have width over time, where length stays constant. So width over time is distance over time, meaning we can replace that piece with velocity. Let's go ahead and summarize it using only variables. Here we have a loop of wire of length L and a resistance R. It is moving at a speed v through a magnetic field of magnitude B. Answer this question in terms of B, L, V, and R. Again, our EMF is just going to be B, L, V. Our current, which is I, is equal to our EMF over R. So we can actually leave it in terms of B, L, V over R. Now these are important so that you can do the multiple choice a lot faster. Here we're asked for rate that energy is generated, which is just power. We said before that power is equal to current times voltage. In this case, current is BLV over R, what we saw in the previous example. Our voltage, or EMF, is going to be BLV. So if we simplify this, this is B squared L squared V squared over R. And then finally, we're asked to determine the force needed to keep the loop moving at a constant velocity. Again, we said that this force is going to be equal to our magnetic field, which in this case is ILB sine theta, where theta is equal to 90. Our current is from before, BLV over R. Our B and L and B are variables that we can use in our final equation. Again, we get B squared L squared V over R equals F. The force needed to be applied in order to move it at constant speed. And finally, we have Lenz's law that states that the magnetic field of the current carrying wire, which in this case is the red loop, is going to oppose the change in the magnetic field that created the current in the wire. Again, go ahead and write this part down and we'll see examples of what it means. So down here, we have this red wire that's moving into the blue magnetic field. As this red wire goes into the magnetic field, the amount of X's is going to increase. So again, Lenz's law says the current created in the red wire has to flow in the direction that opposes the change of the blue magnetic field that takes place inside the red loop. So let's say we have this red wire going to this magnetic field. We've already seen that we're going to have a current that goes in this direction, okay, if the velocity is moving to the right. That means if you use your other right-hand rule, that my magnetic field is going to be going out of the page. So we're going to represent this by red dots. So the magnetic field created by the red wire is shown by the red dots. So again, my magnetic field by the wire is going to be in the positive Z direction, whereas the magnetic field that's already there is in the negative Z direction. Again, as it's going into the magnetic field, it wants to oppose the magnetic field that's happening on the inside. Now, what if the wire is pulled back out? Well, again, the previous right-hand rule that we saw in this problem, in this video, tells us that our direction of the current is now going to change because the force is going to push the charges in the opposite direction. Well, that means if you were to use your other right hand rule that tells us that my thumb goes in the direction of this current, I'm going to have a magnetic field that goes into the page here. Okay, now represented by X's. So my magnetic field by the current carrying wire is now in the negative Z direction. My magnetic field by the blue piece is still in the negative Z direction. But the reason that they're in the negative Z direction is because this is going down. So to oppose that change, we need to increase our magnetic fields in that direction. Over here at the top, as my magnetic field was increasing, we're opposing that change, so we're canceling it out. So let's try it another way. Here we have a current carrying wire that is going upwards, and it has an increasing current. Okay, so that means I'm going to create a magnetic field due to this particular wire. Again, using my right hand rule, that tells us that on the right hand side it goes into the page, and on the left hand side it goes out of the page. Now, we did say that the current was increasing. What that means is as my current increases, I'm going to have more and more X's appear on the left hand side. And we'll have more dots appear on the right hand side, but we're not focused on that part right now. So this red wire is going to oppose that increase. The only way to oppose that increase is by creating a magnetic field that is in the opposite direction. Now, using the right hand rule, in order for us to have a magnetic field in that direction, that means we have to have a current going in the clockwise direction. So let's say we have a current carrying wire that has a decreasing current. So first off, we can use our right hand rule. That means that we're going to have it go into the page on the right hand side, and then out of the page on the left hand side. Okay. Again, we have a wire of conducting material. Now, as we have a decrease in current, that means some of these dots are going to start disappearing. In order to cancel that out, in order to cancel out that decrease in magnetic field, we're going to have an increase in magnetic field created by the red wire. The only way to increase it is by adding a magnetic field in that direction. Now, in order for us to have a magnetic field in that direction, we must have a current going in the counterclockwise direction. Again, this is happening because we have a decrease in current in the blue wire.